In this appendix video, we fill in a few math details for the 11th installment in the Relativity series. To begin, we look at the relationship between the Newton and Einstein theories of gravity. We'll work in rectangular coordinates, traditionally denoted x, y, and z, but in our notation, x1, x2, and x3. A corresponding velocity, ui, is the change in that coordinate over the change in time, the rate of change of the ith coordinate. In classical theory, a gravitational potential U is assumed to exist at every point in space. This equals the amount of work required to move a unit mass from some reference point to the point in question. On Earth's surface, and using sea level as the reference, this is simply proportional to ground elevation. The equation of motion for the ith coordinate is the rate of change of the ith velocity, acceleration, equals the negative of how fast the potential changes with the ith coordinate. In the Earth analogy, if the potential increases with an increase of a coordinate, then you're going uphill in that direction. The minus sign says that gravity will accelerate you in the downhill direction, and the steeper the uphill slope, the larger the downhill acceleration. In empty space, the law of gravity is that the sum of the curvatures of the potential in the three spatial coordinates equals 0, which is called Laplace's equation. We want to compare the classical theory to the Einstein equations in the low velocity, low mass limit. This is the regime where Newton's theory is spectacularly successful. So for relativity to be valid, it must reduce to Newton's theory in this limit. Relativity is based on the idea of a space-time metric with components g, I, j, such that ds squared equals the sum over I and j of gij, dxi, dxj. ds is an interval of proper time. The elapsed time measured by a clock that moves through the coordinate changes dxi. Velocity ui is the change of coordinate I over change of proper time. The low velocity limit is the case where u1, 2, and 3 are all much less than 1, which in our units is the speed of light. So all velocities are much less than the speed of light, a condition which is certainly true for scenarios where we would typically apply the Newtonian theory. The fourth velocity is the change of coordinate time t, or x4, with respect to proper time. For clocks that run at significantly different rates requires high speeds and or extreme gravitational fields, both of which we are assuming is not the case. So we can assume that u4 is nearly 1. The low mass limit assumes that the metric is almost that of flat space-time, shown here. We'll represent the small changes due to gravity as a tiny parameter a times a set of additional coefficients hij. Plugging this into our metric equation and dividing through by ds squared, we get the results shown here. Now, u1, u2, u3, and a are all small, and we'll neglect the product of two or more small quantities. So the first three terms on the right side of our equation can be neglected. For the last summation term, a is small, so if I or j is 1, 2, or 3, we'll have the product of small quantities, a times u1, 2, or 3. Therefore, the only non-negligible term will be I equals j equals 4, and we arrive at an equation that only involves u4 and h44. Relativity's law of gravity in empty space is that all 16 components of the Ricci tensor vanish. By a similar argument, only the R44 term will appear in non-negligible expressions. So it's enough to require simply that R44 vanishes in the low velocity, low mass limit. We'll call H44 2u. U will turn out to be proportional to the classical gravitational potential. The equation on the second line then requires that u4 equals 1 over square root of 1 plus 2au, which is well approximated by 1 minus au. Now we simply plug these ideas into our relativity maxima code. We declare that the function u depends on the four coordinates, and we add 2au to the g44 component of the flat spacetime metric. Then we run the code and look at the resulting Ricci tensor. Specifically, we neglect terms in a to the second and higher powers using a so-called Taylor series. We see that the R44 component vanishes if au satisfies Laplace's equation. Continuing on to the equations of motion, the first three contain a factor u4 squared times a. which in our approximation is just a. So the equations of motion read that the ith acceleration equals minus the rate of change of AU with the ith coordinate, for I equals 1, 2, and 3. Therefore, we've recovered both the Newtonian equations of motion and the equation of gravity in empty space as the limit of Einstein's equation when velocities and masses are small, provided we identify AU with the Newtonian gravitational potential. The Schwarzschild solution is best expressed in spherical coordinates. For a point with given x, y, and z coordinates, we draw a line from the origin to the point. The length is the r coordinate, and the angle between the line and the z-axis is the theta coordinate. The angle between the x-axis and the projection of that line into the xy plane is the phi coordinate. In special relativity, the metric relation is ds squared equals dt squared minus dl squared. And in spherical coordinates, dl squared is dr squared plus r squared d theta squared plus quantity r sine theta squared d phi squared. We use our index coordinate notation with x1 equals r, x2 equals theta, x3 equals phi, and x4 equals time t. We can then place the various metric coefficients into the metric tensor to get a description of flat spacetime in spherical coordinates. Before we look at the Schwarzschild solution, let's look at the low velocity, low mass limit. The Newtonian potential of a mass m is minus m over r, or minus m over x1 in our notation. We add twice this to G44 to get a metric that will describe Newtonian gravitation outside a spherically symmetric mass m. The only difference in Schwarzschild's exact solution is that G11 is divided by this same 1 minus 2m over x1 expression. Plugging this into and running our maxima code, we find the Ricci tensor vanishes without any approximations. Continuing on to the equations of motion, and limiting consideration to the equatorial plane, theta equals pi over 2, we get the results shown here. For the important special case of circular motion, x1, which is the radial coordinate r, is constant. So the radial velocity and acceleration are 0. With u1 0, the last two equations reduce to 0. And the first equation, after canceling a common factor, reduces to u3 squared equals m over x1 cubed times u4 squared. From this, we get u3 over u4 equals 1 over x1 times square root m over x1. It could also be the negative of this, corresponding to a circular orbit in the opposite direction. The velocity of the circular orbit, according to the bookkeeper, is r d phi over bookkeeper time increment dt. We write this as x1 dx3 over ds times ds over dt. u4 is dt over ds, so ds over dt is 1 over u4. And the bookkeeper velocity is x1 times u3 over x4. Using our solution for u3 over u4, this reduces to square root m over x1. The orbital velocity according to a local observer is r d phi over dt local, which we write as the bookkeeper velocity times dt over dt local. dt local equals square root 1 minus 2m over x1 times dt. Using that, we find the local observer velocity is square root m over x1 minus 2m. Finally, we look at the special case of radial motion, where the angles theta and phi remain constant and the corresponding velocities are 0. The equations of motion reduce to the form shown here. For an object falling from rest, that is, with u1 equals 0, the first equation for radial acceleration reduces to minus u4 squared times m over x1 squared times 1 minus 2m over x1. Since the metric requires the following relation, and all the u's except u4 is 0, we can solve for u4 squared equals 1 over 1 minus 2m over x1. Substituting this into the equation above, we find that the radial acceleration is minus m over x1 squared.